Hi, everyone. Thank you for coming back. Our next speaker is David Plaza, who from the University of Talca, who is going to tell us about combinatorial invariance conjectures for A2 tilde.
Okay, thank you, Nicole, and all the organizers for the invitation. My talk is about the combinatorial invariance conjecture for an affine Weyl group of type A2 tilde, and this is a joint work with Gaston Bourroul and Nicolas Libedinsky. Okay, my talk is divided into 3 sections. In the first one, I will introduce the conjecture, the combinatorial invariance conjecture. Then I will present some formulas for casuistic basis elements in an affine Weyl group of type A2 tilde. And in the last section, I will present some ideas we used in the proof of this conjecture. Okay, so the conjecture relates the Brouhat order in a Coxeter system with Kasten-Lustig polynomials. So I need to recall some stuff about Coxeter system and Hickey algebras, and some of these first slides intersect with the first slide in Christian's talk. But anyways, a Coxeter system is a pair where W is a group and S is a finite set, and W admits a presentation of this form. So the generators are the elements of S, and they are involutions, and they satisfy this type of relations. And a Coxeter system comes equipped with an order, and this is the Brouhat order, which we denote by this symbol, and it also is equipped with a length function L. The length is defined as follows. So each W in W can be written as a product of the generators. And if K is minimal in this expression, we define the length of W as K. And in this case, when K is minimal, we say that this expression is a reduced expression for the element W. And Brouhat order can be defined in terms of reduced expressions. So given U and B in W, we say and write U less than or equal to B if and only if there exists a reduced expression for B such that we can obtain a reduced expression for U by eliminating some letters here in this reduced expression. Okay, for any Coxeter system, we can associate a Hickey algebra, which we denote by H, and this is the ZBB-1 algebra generated by symbols HS, where we have one algebra generator for each group generators, and this generator satisfies 2 types of relations, the quadratic relation and the braid relation. And as in Christian's talk, we have a standard basis that is defined for any x in W. We consider any reduced expression for x, and we define the element hx by replacing in the reduced expression group generators by algebra generators. And this is a basis. But in order to define Kasten-Lustig polynomials, we need to consider another basis, the Kasten-Lustig basis of a Hickey algebra. And this was introduced by Kasten-Lustig in '79. And so if W is any Coxeter system and H is its corresponding Hickey algebra, we consider a Z linear map D from H to H given by these 2 conditions. This D is what Christian called the bar involution. And so for any W in W, we have a unique element, H bar W, given by these 2 conditions. So we have that H bar W is invariant under the action of D. And also when we write H bar W in terms of the standard basis, we have a triangular decomposition, and also the polynomials occurring in this decomposition belong to BZB. And because of the triangularity, it's clear that this is a basis for the Hickey algebra, and these polynomials are the well-known Kasten-Lustig polynomials, but they are the Kasten-Lustig polynomial in Sorgel's normalization. And the original Kasten-Lustig polynomial Pxy as defined by Kasdan and Lustig, are slightly different, but the H version of these polynomials and the P version of this polynomial is related by this equality. So we can pass from one version to another very easily. And we will make use of both versions during this talk. So we have already defined all the ingredients needed to enunciate the combinatorial invariance conjecture, which is due to Lustig and Dyer independently. And this conjecture claims that if we have two Brouhat intervals that are isomorphic, xy and x prime y prime, isomorphic as posed. So I mean there is a bijection, an order preserved bijection between these two intervals, and then the corresponding Kasdan-Lustig polynomial must be equal. Okay, so I think that if this conjecture is true, this would be quite surprising, and this is because we can reformulate the conjecture by saying that in a computation of a Kasdan-Lustig polynomial pxyq, the only information needed to perform this computation is the one in the Brouhat interval, but I mean in the unlabeled Brouhat interval. So if the conjecture is true, we should be able to compute a Kasdan-Lustig polynomial only using the information contained in a diagram like this, but we are not allowed to know we are not allowed to know x, y, or even the group where x and y live. And this sounds, I mean, Kasdan-Lustig polynomials are an interesting object of study because they encode some geometric and representation theoretic information. And I think it seems unlikely that this information doesn't depend on x and y, but only on the isomorphism type of this posed. And this is the reason why some people think that the conjecture is not true. On the other hand, we have some result that provides some evidence in favor of the conjecture, and the strongest result in this direction is the one by Brenti, Caselli, and Marietti, and they prove that this conjecture is true for lower intervals. And here lower means intervals starting from the identity. So if both intervals involved in the conjecture are lower, then Brenti, Caselli, and Marietti prove that they are equal. And we have some other results, some other partial results concerning this conjecture, and I would like to mention this result because we use this specific result in our proof of the conjecture for an affine Weyl group of type A2 tilde. So this result is that if we have an isomorphism between two intervals, Brouhat intervals, and the length of these intervals defined in this way is less than or equal to 4, then the Kasdan-Lustig polynomial are equal. So we know that the conjecture is true under this extra hypothesis.
Sorry, can I interrupt? What are E and E prime in the theorem of the first theorem here? Or what's the hypothesis in the first theorem?
In the first or in the second?
The first one.
It's the identity of the group.
And E prime, I guess, is also the identity of...
Oh, yes. But this is a striking feature of the conjecture. Both Coxeter system could be different.
Okay. Sorry,
so
I see.
Okay, so here we have our main theorem, that is, we prove the conjecture for an affine Weyl group of type A2 tilde. So we add some new piece of evidence in favor of this conjecture. And I would like to mention that this is the first infinite group with non-trivial Kasdan-Lustig polynomial where the conjecture is verified. Okay, so the main the main tool we used in our proof is some results by Libedinsky and Patimo last year, where they obtain explicit formulas for Kesdelustic basis element and then for Kesdelustic polynomials for an affine Weil group of type A2 tilde. So from now on, we specialize W to be the affine Weil group of type A2 tilde, and this is the group generated by 3 generators, S0, S1, and S2, and it has this Coxeter presentation. And for simplicity, it is useful to denote the generators just by numbers 1, 2, and 0, and also is useful to use a label mod 3 notation. Okay, and okay, Libedinsky and Patimo's formulas are divided into 4 cases, and so we need to split or partition or group into 4 subsets. And to define this partition, we need to consider certain bijections on W. The first one is the map rho, which can be defined in the generators of the group, and it's just a rotation. It rho sends S0 to S1, S1 to S2, and S2 to S0. And sigma is the map that fixes S0 and permutes S1 and with S2. And they can be extended to automorphism of W, and we denote them by the same symbols. The last bijection we need to consider is the inversion anti-automorphism, which we denote by iota. And then we consider the group G as the subgroup generated by rho, sigma, and iota as a subgroup of the symmetric group on group W. Okay, it is convenient for visualize the partition of this group into 4 regions to recall the realization of our group W as an affine Weil group, or as a group of affine reflections, in this case in the plane. So in this setting, we consider the tessellation of the plane by equilateral triangles and fix any triangle. In this case, we fix this yellow triangle and declare it as the identity triangle, and then consider the lines that support the sides of this triangle and the reflection through these lines. So we consider here we identify each one of these reflection with our generator. So we identify the reflection through this blue line with S0, this green line S1, and the reflection through this red line with S2. And in this setting, each triangle corresponds to a group element. So for instance, this gray triangle, to see which element corresponds to this gray triangle, we need to draw a path from the identity triangle to this guy, this gray triangle, and then we need to look to the colors we cross in this path. So in this case, we have green, blue, red, green, blue, green, red, blue, and this gives us a word in our generator because of the identification in the previous slide. So this way we have defined a bijection between the set of triangles and our group. So in what follows, we do not distinguish between triangles and group elements. Okay, so our goal is to define a partition of our group in 4 regions. The first region is region X, and to define region X, we need to first define elements Xn, and these are 1, 2, 3 till n. And remember that we are working using label mod 3 notation. So this is just 1 to 0, 1 to 0, 1 to 0, and so on. And geometrically, these element Xn are represented by these triangles. Geometrically, this is 1 to 0, 1 to 0 translates to green, red, blue, green, red, blue, green, red, blue, and so on. So we have this line. In this line, we see all the Xn. But to define the region X, we want to consider elements Xn, but also we want to consider their G orbits. So the formal definition or algebraic definition of region X is this, and the graphically this is the region X, our first region. The second region is region theta, and as before, we start by defining certain elements. In this case, for any pair of non-negative integers, mn, we define the element theta mn, that is 1, 2, 3. So we start by 1 and go up till 2m plus 2, and then go down till 2m minus 2n plus 1. Graphically, these elements theta mn correspond to these black triangles. And as before, to define the full region theta, we want to consider these triangles and their g orbit. So this is the definition, and graphically we get this region. The second region, that is region theta. The third region, region theta 1, is defined as follows. So first, we need to notice that for any theta mn, there exists a unique simple reflection, which we denote by SMN, satisfying this inequality. And so we first consider the elements theta mn smn, which correspond to these gray triangles. And then, as before, we consider their g orbits. So region theta 1 is defined this way, and graphically, region theta 1 correspond to all these gray triangles. The last region, region theta 2, is defined similarly. In this case, we first consider elements S0, theta mn, SMN, and their g orbits. And graphically, these correspond to the white triangles in this picture. So just to summarize, from lightest to darkest gray, we have region theta 2, x, theta 1, and theta, and the yellow triangle, the identity, doesn't belong to any region. Here, we are making the convention that the lightest gray is white and the darkest gray is black. Okay, so we have partitioned our group into 4 regions, and we are almost ready to present Libedinsky and Patimo's formula, but we first need to consider 2 ingredients. First, this lemma that reduce the number of formulas we need to specify, because this lemma tells us that Kassan-Lustig polynomials are invariant under the action of group G, and this allows us to only care about elements, Kassan-Lustig basis element indexed by xn, theta mn, smn, and s0, theta mn, smn. Okay, so now we define 2 elements, the n elements and the m elements. So the n element is defined for any x in W, and it's just a sum of standard basis element times a monomial, and this sum runs over the lower interval associated to x. And the definition of m is similar, but in this case, we consider 2 elements x, y in W, and rather than sum over the lower interval, over 1 lower interval, we sum over a union of 2 lower intervals, the ones associated to x and y. And okay, finally, we can present the formulas by Libedinsky and Patimo. These are the formulas for region X, or our first region, and you can forget these formulas immediately. Yeah, my point here is that from the beginning of the theory, we have an algorithm to compute Kassan-Lustig polynomial, but the problem with this algorithm is that is recursive. So it's too slow, this algorithm. And these formulas allows us to compute a Castells-Lustig polynomial in a non-recursive way. So we have a direct access to Castells-Lustig polynomials. So these are the formulas for region X, and these are the formulas for region theta. This is a very nice formula, very easy, just a sum of n elements. And they also provide formulas for region theta 1, region theta 2, and with these formulas, we can compute Castells-Lustig polynomial in a non-recursive way, but we don't like these formulas for this conjecture because we are still using an algebraic operation in order to compute a Castells-Lustig basis element. So here, in order to obtain a Castells-Lustig polynomial in region Castells-Lustig basis element in region theta 1 or in region theta 2, we need to make a multiplication. And the spirit of the combinatorial invariant conjecture is it's a combinatorial conjecture. So we need to avoid any algebraic manipulation in order to compute these elements. Okay, so we slightly improve formulas by Libedinsky and Patimo and provide these formulas for region theta 1. And in these formulas, I want to point out that here we first we need to separate in different cases according to the value of m and n. And in these formulas, we can see some n elements and also some Castells-Lustig basis element. So in order to compute a Castells-Lustig basis element in region theta 1, we need to compute a Castells-Lustig basis element in some region. But if we look at the index of this element, they are theta elements, so they belong to region theta 1. So we can go back to the last slide and use this formula to compute the element. So this is indeed a non-recursive way to compute this element. Okay, and for region theta 2, the situation is similar, but here as before, we have to separate in 4 cases, and as before, we see some n's. Here we have some m elements, and also some occurrences of Castells-Lustig basis element, but all of them are indexed by element in the previous region theta 1. So as before, the computation of a Castells-Lustig basis element on region theta 2 relies on the computation of a Castells-Lustig polynomial in region theta 1, and this in turn relies on the computation of a Castells-Lustig basis element in region theta. So this is the nicest formula. At the end, in region theta 1 or region theta 2, at the end we use this nice formula. Okay, so we have non-recursive formulas for Castells-Lustig basis element, and using them we can compute Castells-Lustig polynomial in a non-recursive way. So let me now to show some ideas we use in order to prove the combinatorial invariance conjecture. And the first step, we need to understand what these formulas are telling us. So we can summarize all these formulas by saying that in order to compute a Castells-Lustig polynomial, we can avoid any computation in the Hickey algebra. So the only tool we need to compute a Castells-Lustig polynomial in this group, of course, is the Bruhat order. And let me illustrate this with an example. So suppose we want to compute px theta 32, or equivalently hx theta 32. Okay, and in any case, we need to focus first on the second index of a Castells-Lustig polynomial and use the corresponding formula for the Castells-Lustig basis element. Here is a theta 32, so we need the formula for theta mn, and the formula for θ32 reduced to this sum of 3 n elements. And we can make the computation graphically as follows. So remember, so these n's are indexed by θ32, θ21, and θ10. This triangle is the one corresponding to θ32. This triangle is the one corresponding to θ21, and this corresponds to θ10. And here we have to remember that the n element was defined as a sum of standard basis element in the lower interval associated to x in general, in this case θ32, θ21, and θ10. So in order to perform the computation, we need to draw the lower intervals associated to θ32, that is this region, the lower interval associated to θ21, that is this region, and the lower interval associated to θ10, that is this set. Notice that till this moment we have not used the index, the first index, in this case x. But of course, the exact value of the Casan-Lustig polynomial will depend on this x. And for this example, we have the following formulas for the Casan-Lustig polynomial. So we have 4 cases. A Casan-Lustig polynomial in this example could be 0, 1, 1 plus q, 1, or 1 plus q squared. And it depends on the location of x in this picture. For instance, if we consider this picture, so this polynomial, we consider a triangle of this color. And this means a triangle in this region. And any triangle in this region, it's then, so the Casan-Lustig polynomial associated to any triangle in this region, it's equal to 1 plus q. And the point here is that any of these 4 regions, the white region and this gray region, this intermediate region and this light gray region, can be defined in using only the Bruhat order. So for instance, this region here correspond to the elements that are less than or equal to θ21, but are not less than or equal to θ10. So we have indeed reduced the computation of Casan-Lustig polynomials to a process in which we use only the Bruhat order. So what is missing to prove the conjecture? We have reduced the computation only to a Bruhat order problem, but the problem with this way to compute Casan-Lustig polynomial is that we are still using the names of the elements. So when we compute in the previous slide an example, we say θ21, θ10, θ32, or whatever. So the conjecture tells us we are not allowed to use the specific values of the elements involved in the Casan-Lustig polynomial. So we need to compute a Casan-Lustig polynomial only using the unlabeled Bruhat interval. And to do this, we need to define some poset invariants. And the first poset invariant is what we call the set invariant. And to define it, we need to first define the set zxym, which is formed by all the set in the interval xy, such that the length of y minus the length of z is equal to m, and such that the Casan-Lustig polynomial pzyq is 1 plus q. And the cardinality of this set is a poset invariant if m is less than or equal to 4. And this is because the result I mentioned in the first section, that we know that the conjecture is true for intervals of length less than or equal to 4. So in this case, when m is less than or equal to 4, we know that the cardinality of these sets Z are is a posed invariant. And this is our first invariant. And the second posed invariant we consider in the proof is the notion of two parents. So the two parents, it's the definition of two parents is as follows. We consider any interval x, y, and we fix some elements a and b in the interval x, y of the same length. And an element z is called a two parent of a and b in the interval x, y if z belongs to the interval x, y, is greater than a, is greater than b, and the difference of length between z and a is equal to 2, and the same for the difference of length of z and b. Okay, and we denote by this symbol the set of all two parents of a and b in the interval x, y. And okay, and as before, the cardinality of this set is also a posed invariant. Okay, so we have two posed invariants, that the set invariant and the two parents, and this together with monotonicity, with the monotonicity of Castellustic, the monotonicity property for Castellustic polynomial that claims that if we have three elements u, b, and w, such that u is less than or equal to b and b is less than or equal to w, then this difference of Castellustic polynomials must have non-negative coefficients. So summing up, in order to make our computation free of names, we use these two invariants, the set invariants, the two parents, the monotonicity property, an inductive argument on the length of the intervals, and we need also a case-by-case analysis of the formulas in order to obtain the proof of the conjecture in this case for an affine Weyl group of type A2 tilde. Here, I mean case by case, we start with a pair of isomorphic intervals, and we need to consider different case according to the location of y and y prime in the different regions we have defined previously. So of course, there are many technicalities in this analysis, but at the end, we were able to prove that in any case, if the intervals are isomorphic, we must have the equality between the Castellustic polynomials. And okay, that's all. Thank you.
Thank you very much. Does anyone have any questions for David?
Will you try to do B2 tilde next?
I think that the obvious step is A3 tilde, but we don't for A2 tilde we have two main tools. On the one hand, the formulas, and on the other hand, this theorem. And this is not, and for A3 tilde, apart from the formulas, that it's a complicated problem, and we should have something like this theorem, but for greater than 4 or 6. For some reasons, because we know many of the formulas in A3 tilde, and we need a result like this. But this result is not available in this moment.
Do you need that result for A2 tilde slash B2 tilde? What do you need that result for? I'm sorry.
So, sorry, Karina?
This last result that you were mentioning, the difference being less or equal than 6, what do you need it for? Which case do you need it for? A3?
For
tilde?
A3 tilde. For A3 tilde.
Okay.
And I think it's also, we also need this result for B2 tilde.
Okay.
All right. If there are no more questions, we can thank our speaker and then stop the recording.